Welcome to Brain Vision.
Now at this point, you want to substitute in the energy of the electron, total energy of the electron, as using the Einstein's mass energy relation. This equals to square roots. Sorry, no square roots. This equals to P E square C square. Sorry, P E prime C square plus the rest energy squared. And this is actually, if we were to substitute in the PE is actually equals to P prime, sorry, PE minus P minus P prime. And what we really want is this PE C square plus M square C4, because that is the original total energy of our electron. And the remaining terms is actually just a mixture of P and P primes, as well as the PE. So we're gonna bracket this up together. What we'll get is 2 times PE forgetting the C squares. And now we're going to substitute that into this expression. And we see that this is equals to square root of this expression over here. What we're going to do to open up this square root is to bring this P prime C to the left. So we have P minus P prime C plus E, and we're going to square both sides. So we square both sides, then the brackets will open up. And one of the interesting things is that the E square term will cancel out. So we have P minus P prime square C square. Because this is a plus E, so we will plus 2 times of P minus P prime C times E plus E square is equals to E square along with the rest of the terms, which is minus PE these square terms cancels out, and then we see that this gives us p squared plus 2p p prime plus p prime square, and this one gives us p squared minus 2p p prime plus p prime square. Right? They both multiply by c square, so actually their square terms will cancel out as well. And then we can bring this over to the right hand side. So what we really have left is 2 times p minus p prime c times e is equals to 4p times p prime c square minus 2pe p plus p prime c square. And now to really solve for this, we need to bring all the p primes to one side, so only the p prime terms. So we have this negative 2pe p c square, which is going to bring to the left hand side. We're going to divide everything by 2. So divide everything by 2. And we will factorize out the p prime. This is the remaining terms, which we're going to bring to the left hand side. So this is the expression that we have, and it's not very pretty, definitely, but what we'll try to do is to now find the wavelength. So it's given as h over momentum prime. So we'll multiply by the inverse of this. And of course, to simplify even further, we divide everything by c, since we have a common factor c. Right, and it's looking quite simple now, but of course we're not done yet. To simplify it further, see if we can find any common factors. Right, so like we have P, we have H over original momentum P, taken from the denominator, and then at the numerator we have some common factors. So this lambda times E minus PEC plus 2 times of PC divided by E plus PEC. Now we know that PC over here, PC is given as the energy of the gamma ray, energy of the photon, sorry, which is given as hc over lambda as well. So if we multiply in lambda with this PC, what we get is just hc, right? So we can multiply this in to get lambda plus 2hc divided by E plus PEC. This is the final expression and the easiest expression, most simplest expression. Now with this expression, we're now gonna put in the assumption that E is much greater than mc squared. Now what will this assumption do to our expression, right? So one of the things is that we know that E square is equals to PE square C square plus M square C4. So if you were to find P square C square, this actually equals to E square minus M square C4. We take the square root of this. We factorize out E. We can actually do a Taylor expansion or binomial expansion of this expression. Since E is much greater than mc square, it means that mc square divided by E is less than 1. Right, so we can do a binomial expansion. This is approximately equals to E1 minus square C4 divided by E square times half. Sorry, it's supposed to be, yep. And so with this, we ignore the higher order terms, because that would be when we have m to the power 4, c to the power 8, etc. And that is very, very small, much smaller already. So we don't have to ignore, we can ignore them and just truncate at the first order. And from here, right, we can use this approximation to simplify our numerator, which is E minus PEC, as well as the denominator, E plus PEC. So what are they, right? So E minus P, sorry, to be E minus E plus m squared C4 over 2E. And this will give us m squared C4 over 2E. Right? On the other hand, for E plus PEC, this will be E plus E minus square C4 divided by 2E, which in this case we have two terms, right? We have 2E minus m squared C4 over 2E, and because this term is much smaller than E, we can approximate this to just be 2E, right? Just one first order. And we got to put this into the expression for our lambda prime, which I've written already. I've written down here. So E minus PEC, this is m squared C4 divided by 2E, and E plus PEC is approximately just 2E. And further simplifying this expression, we bring down the E2E value here. Right, so actually this terms we can separate out. We can get the common terms, which is HC over E. So this factor right here, gotta simplify this into HC over E. So this is lambda m squared C4 for E squared plus HC over E. To convert this into the equation that was given in our question, we will try to factorize out HC over E from both terms. So from the second term, this is just 1, and then the right hand side, we will need to reduce the C power by 1, and then we will add 1h at the denominator. So this is the expression given in the question. Finally, to put in some of the values that is given, put in numerical values. We have a beam of radiation with the wavelength of 10.6 micrometers, and we are given that the total energy, initial energy of our electron to be 10 GeV, or just 10 times 10 to the power 9 eV. Because this energy is much greater than the rest energy of the electron, which is 0.511 MeV, which is just 5.11 times 10 to the power 5 eV, right? Much greater. So the assumption holds, right? The assumption that we have made previously holds. So the lambda prime can just be written down as hc over E 1 plus m square c cubed lambda over 4h e. And evaluating this expression, we should get 7.08 times 10 to the power minus 15 meters. Now this particular radiation wavelength is in the gamma range, the gamma ray region, which is a very different compared to the initial wavelength of 10.6 micrometers. Right, this is from the infrared, and we have actually converted from infrared to gamma rays. And this is particularly effective if we want to have controlled sources of gamma rays, right? Where we want to have gamma rays such as in nuclear medicine or high energy physics, right? Because of this process, we can actually produce gamma ray sources.